Okay. Right. So from here, where you know our area, then we want to find our y bar. So our y bar is equal to c plus y multiplied by 0.5, half of it. So I've shown last week y, so I'll repeat again. If this is 6, okay, that is 10. Without using the formula, you know that the distance from C prime, okay, you know this distance is equal to what? 8, right? So why is it equal to 8? So that's by observation. If you put in the formula, it's 10 plus 6 multiplied by 0.5. This is also equal to 8. So that's the central distance. So from here, we can write down that the first moment of area about the z-axis is equal to b c minus y c plus y multiplied by half, or 0.5. So if I were to tidy things up, so this is equal to 0.5 b bracket c squared minus y squared. Okay. So rule number 4, right? Rule number 4 that I'm going to state, right? Without the mathematical relationship is the first moment of area. So rule number 4 is the first moment of area all right, the first moment of area cannot cross over or intersect the centroid. Okay, so there's a four. Now let me elaborate what do I mean by that. Okay, let me elaborate what do I mean by that. All right, so now if we were to have a again the same structure, okay, I'll copy the same thing. I can't copy now. All right, so we have the same structure. All right, so now what do I mean by the first moment of area cannot? So let's say now, right, our shear stress, our shear force is still acting in this direction, Vy. Okay. So now I'm interested to find the shear stress at a point written down here, known as alpha. Okay, that is our point. That's our point of interest. I want to know what is the shear stress of alpha. So because we are so engrossed, right, or we are so focused on Vy, you say, okay, right, we are going to do this. Okay, we are going to find first moment of area, right? So you're the area that you're going to take, right? You say, okay, so Vy, you're so fixed into Vy. Okay, you're so fixed into Vy now, right? And you want to find the point alpha, and you realize, okay, because of the point alpha that I'm going to find, this is the area that we are going to consider. Okay, and this is wrong. Any idea why this is wrong? Anyone, please? Anyone, why this is not correct at all? No?
Because you know one of the rules about intersecting the
Yeah, you cross it, yes or no? You cross it, and 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 when I started doing this, I also had in my mind when I don't set the rules, because Vy is coming on, the shear stress has to be coming from the what? From the top to reach what? Alpha, yes or no? Right? Mechanical engineers. Seeing is what? believing. Yes or no? There you go, right? Not necessarily true, right? So that is wrong because we broke what? Rule number what? 4. Because we cannot find the first moment. So the first moment of area, the axis, where the axis is, the moment is going to rotate, the moment area that's going to rotate is about the z-axis. You cannot intersect the rotation moment. So the only way to do this is, no doubt, your shear stress, your shear force is still coming up from vertical. It's still coming up from the top, right? So this is Vy. And if the point of interest is alpha, the correct area to analyze is here. And this is because of how we calculate the what? First moment of area. So this is right. Okay, and the other one is wrong. Okay, that's why, remember what I told you, there's only 2 formula for this course. The analysis is the one that's most critical, and the analysis you have to obey what? These 4 rules. So I just show you one example. Okay, so once you know these 4 rules, okay, and I teach you how to find the first moment of area, after today, chapter 6 you can do from the first question up to the last question in the textbook, up to the last section. Given prismatic geometry, as in fixed geometry, you can solve everything. Okay, that is the power of setting rules like that, right? At McMaster, we don't teach Mickey Mouse stuff, we teach serious stuff. Okay, right? So coming back to here, so we have formed our first relationship where TZ is equal to QZ is equal to 0.5 BC squared minus Y squared. So the next thing that we're going to do now, I'm going to go back into this figure again, right? Do I need to go back to this figure? Let me see. Do I need to? Yeah, I'm going to paste the figure on the next page. Right.
Gene, I just have a question about the first moment of area.
Yes.
So if you go back to the calculation, why did you how did you get c plus y times half? Like you said, because you look at the bottom.
So yeah, so the y prime is the centroid, yes or no?
Yeah.
Of the area of interest. So
Yes.
if I put 10 over here, if I put 6 over here, geometrically by observation, you know that this is 8. Am I right?
Yeah.
Right. So what's the formula? C plus y multiplied by half.
Okay. All right. So you just plug in some numbers to find out the equation type thing.
Yeah. Okay. Why I do that? Why I put in numbers for you guys? Because I don't want you all to memorize. Okay. I want you all to okay, how to get a centroid is just simple way. Just plug in the numbers and you can see it for yourself. Does that answer your question?
Yes. Thank you.
Good. Right. So from here, again, our shear stress, shear force is coming from Vy. So the formula now, so now the next thing we want to find is Izz, right? So the ZZ axis is of interest. And like what I taught you guys before, parallel to the geometry in the ZZ, this is the width, and perpendicular, this is the depth. So your Izz, the width is B, the depth is 2c cubed over 12. So this is equal to 8 over 12 BC cubed. And this will be equal to 2/3 BC cubed. Okay. So now we're going to, so we have everything now. So the next thing we want to know is our thickness now, T, right, is equal to B. Okay. So this one, as I written before, right, the thickness over here is a perpendicular geometry orientation relative to the applied shear force, right? So over here, so your Vy is acting in this direction, Vy, so this is perpendicular distance. Okay, so now we have everything. We start putting everything in now. So the shear xy is equal to Vy over Izz Qz divided by T. Okay, so now we put everything in. So your Vy still remain as Vy. Your Qz is equal to 0.5 B C squared minus Y squared. Okay, C squared minus Y squared. Then divide by IZZ. So your IZZ, we have derived this is 2 over 3 BC cubed. And then finally, your thickness over here is equal to B. Right, so it's equal to B. So what we could do is we could strike the B off. And then I'm going to rewrite this expression over here. So this will be equal to Vy, right? 3 over 4. So I is half divided by 2/3 is 3 over 4. Then you have C squared minus by Y squared. And then you over here you have BC cubed. Now we also know based on observation, right? Based on observation, note we are also aware that the area, right? The area of the cross section is equal to 2 BC, right? Because you have C here says 2C multiplied by B is your cross sectional area, so it's 2 BC. So I'm going to cook up the equation. Okay, so I'll still have 3 over here. It's still C squared minus Y squared. Then I'm going to split the 2. Okay, then I'm going to have 2 over here. And then I'm going to bring in BC. And this is C squared. Okay, so this over here, right? And this over here is the same, right? So we are going to rewrite this expression is Vy over A 3 over 2. And we have C squared minus Y squared over C squared. So finally, when we write this out, the shear XY, okay, so the shear XY is equal to 3 over 2A Vy 1 minus by Y squared over C squared. So we realize, so this is the expression that we have derived, like what I showed earlier. So we just derived this expression over here. So what does this actually means? Okay, so as engineers, it's not just, yeah, this is the formula, we're good to go. Okay, it's more than that. Okay, so this is a formula that we have derived. So this is only valid for thick wall. Okay, probably next week we go into, or in 2 weeks time we go into thin wall analysis, or next week, yeah, probably next Thursday we can go into thin wall analysis. So this is only valid for thick wall. And you can see over here, this expression over here, right? This expression over here is always going to be less than 1. So from here, we realize that tau max, the maximum that this expression over here can have is 3 Vy over what? Over 2A. And it will only occur when what? When Y is equal to what? 0. Okay, when Y equals 0. So I'm going to sketch out how the shear stress will distribute. And you know over here, right, this equation over here is a second order polynomial equation. By the way, I'll let you guys know a little secret, okay? Your math is better than mine. I see how you guys are going through 2ZZ03. Wow, okay? It's not easy, so I'll tell you that your math is better than mine. Now, if I take 2ZZ03, I think I will bloody fail. Multiple choice, ridiculous. Anyway, so from here, we're going to sketch this relationship out. Okay. So I'm going to sketch relative to the orientation of our block now. Okay. And I'm going to make you more confused. Not confused, aware. Okay, not confused. Apologize. So the axis I've drawn, this is your shear XY.